Hi, and welcome to Dr. V's Chemistry Webcast. Today we're going to be discussing Bohr's atomic model. Here's what I'd like to accomplish in this webcast. First, I want to talk about the key features of Bohr's model of the atom, and then use the Bohr model to explain atomic emission spectra, which is a really important application of the Bohr model. And then finally wrap up by talking about limitations of the Bohr model and why this model is no longer the accepted model. Studies of light interacting with matter really led to a lot of discussion about the structure of the atom. Let's start by talking about a white light source. If we take the light from a white light source and pass it through a slit, and then pass that light through a prism, we see a full spectrum. However, if we take light given off in a gas discharge tube containing an element, we don't see the full spectrum. We see these bright lines, only certain wavelengths being given off. And so the question becomes, why do these samples give off these sharp, discrete lines and not a continuous spectrum? There was a lot of question about this, and exploring these spectra and trying to make sense of them brought about a lot of important advances in our understanding of atomic structure. Electromagnetic radiation has some very important features that we need to talk about before we go further. One is that light exhibits a wave-particle duality. That means we can think about it as a wave and treat it as a wave with a wavelength. But we can also think about it as particles, so as a photon or a quantum of light. And depending on the situation that you're dealing with, sometimes it acts like a wave, and in other times it acts like a particle. It's worth mentioning that electrons also exhibit this wave-particle duality, and that becomes important as we go further into our study of atomic structure. The work of Max Planck was actually really important in developing a more thorough understanding of atomic structure. Now, we remember Planck from Planck's constant. One of the important ideas that Planck introduced is that energy is quantized when you're on an atomic level, that only certain energies are allowed. We say that they're discrete energies, particular energies. And so this brings us to Niels Bohr, who worked with Rutherford and did his postdoc in Rutherford's lab, and developed an explanation for these atomic emission spectra. Why are we getting these sharp lines and not the full spectrum? He refined Rutherford's atomic model, which was the idea of a nuclear atom. Now, the Bohr model of the atom is probably the most familiar model of the atom. It's the one most of us have as our mental image of an atom. It's got electrons traveling around the nucleus in circular orbits. But what's important about the Bohr model is that only certain orbits around the nucleus are allowed. Electrons are not allowed to be at other distances from the nucleus. So we can have an electron in the first orbit at this particular distance. I called it n equals 1. It can be in n equals 2. We can be in the third orbit. We can be in the fourth orbit. But only these orbits are allowed. And electrons cannot exist at other distances from the nucleus. So we can't be in between an orbit. That's not possible. A useful analogy for these orbits would be the rungs on a ladder. But the rungs are not spaced equally, so the spacings actually get closer and closer as you go up the ladder. And you can only stand on the rungs. It's not possible when you're climbing a ladder to put your feet in between the rungs. That's not something that can happen. You're going to fall down. You can only stand on the rungs in this model. So this is a good analogy. Another important feature of the Bohr model is that the orbits that are farther from the nucleus have higher energy. So if we start in the first orbit, which I've called n equals 1, that's got a lower energy than being in orbit 2, which has a lower energy than being in orbit 3, which has a lower energy than being in orbit 4. We talk about the ground state when the electron is in the lowest energy arrangement. Let's focus on the Bohr model of the hydrogen atom. Now, a hydrogen atom, as you know, has only one electron. So when that electron is in the first orbit, or energy level 1, it's in its ground state. If that electron is in a higher energy orbit, then we say it's an excited state. So if it's in energy level 4, or orbit 4, it's a higher energy position, and we say that's an excited state. One of the most important features of the Bohr model is that it can explain these atomic spectra. So let's talk about how this can happen and what has to happen for an electron to change energy levels. For an electron to transition from a lower energy level to a higher energy level, from a ground state to an excited state, what it has to do is absorb a photon of energy, or it could absorb heat energy as well. But one way to do it is to absorb light. Now, it has to absorb just the right amount of light. So if a photon comes in and it happens to have enough energy to match the energy difference between energy level 1 and energy level 2, the electron can jump to that higher energy state. If a higher energy photon comes in and that photon has the same amount of energy as the energy gap between, say, energy level 1 and energy level 3, the electron can jump from energy level 1 to energy level 3. But it has to absorb exactly the right amount of energy. If it absorbs too much and it would end up between levels, the transition won't happen. If it absorbs too little and it would end up between levels, the transition can't happen. It has to absorb exactly the right amount of energy to make the jump, or the jump doesn't happen. Well, now we have an electron in an excited state. How can it relax to a lower energy level, which of course is energetically more favorable? Well, for that to happen, a photon has to be released, and the photon has to have the amount of energy equal to the difference in the energies of the levels. And so it would have that frequency and the wavelength that would correspond to that delta E. So if we're in energy level 2 and the electron transitions back to energy level 1, it's going to give off a photon. In fact, it's going to give off a photon with the same wavelength as it absorbed to go from energy level 1 to energy level 2, but it has to give away the light to jump to a lower energy level. For that electron that was in energy level 3, for that excited state, it needs to give off a larger delta E to go back to the ground state, to go back to energy level 1, and so it will give off a photon of light with a shorter wavelength and more energy. If it doesn't give off the right amount of energy, the jump doesn't happen. And so we can say energy is quantized. You can only work with these energy changes to make transitions from one energy level to another. You absorb energy to go up to a higher energy level. You release a photon to go down to a lower energy level. Sometimes instead of drawing circular orbits, we just draw the relative energies of the levels. And I do want to point out, much like that ladder analogy, the spacings get smaller and smaller and smaller as you get farther away from the nucleus. So if we have an electron in energy level 5 and it jumps to energy level 1, it has to give off a very large delta E. And that would give off a single line in our spectrum for that transition. So we see these sharp lines in the emission spectra. So the real power of the Bohr model is it explains these emission spectra. So we have a big delta E to go from 5 to 1. To go from 4 to 1, it's a smaller delta E. We're going to give off light with a slightly longer wavelength, maybe a blue line. If we go from 3 to 1, we're going to see a smaller delta E, longer wavelength. And as our delta E's get smaller, the wavelength of that sharp line changes. All right, so we see different lines in our spectrum, these sharp lines, because we're jumping from very specific energy levels, from a higher energy level to a lower energy level, and there's a specific energy difference that is related to that. The transition from energy level 5 to energy level 1 has the biggest delta E of the transitions we're showing here, and so it's got the shortest wavelength, the most energetic light. The transition from energy level 5 to energy level 4 has the smallest delta E of the transitions we're looking at here, and so it's giving off light with the longest wavelength. Remember, wavelength and energy are inversely related, so a big delta E gives a short wavelength, a small delta E gives a long wavelength. So we can say that each line that we see in the emission spectrum corresponds to a specific transition from a higher energy level to a lower energy level, because these are all emission spectra. The specific delta E for that particular transition correlates to a specific wavelength of light. Remember, the bigger the delta E, the shorter the wavelength. The smaller the delta E, the longer the wavelength. The Bohr model is really good for explaining these emission spectra. It does a really nice job with that, but there are some very real problems with this model. One is that classical physics tells us that electrons traveling in circular orbits lose energy. They radiate electromagnetic radiation, and then they would be losing energy. Why aren't they collapsing into the nucleus? Bohr was not able to say why he thought the electrons were only allowed to have specific orbits and why they weren't just falling into the nucleus. Because classical physics would tell us if this is what's happening in terms of these circular orbits, atoms wouldn't be stable and wouldn't exist. But we know that they do. So this idea of the circular orbits at fixed distances doesn't really hold up. And that was recognized very shortly after Bohr proposed his model. Another problem with the Bohr model is that, try as he might, he was not able to predict the emission spectra for multi-electron atoms using his math. It worked great for hydrogen. As long as there's only one electron, it works. He could not extend the math to atoms that had more than one electron, which is a problem because, of course, many elements do have more than one electron. And so it wasn't able to expand beyond hydrogen. And that, of course, is a problem. What do you do when your model doesn't hold up to all the information? Well, you develop a new model. That's a whole different webcast. For a lot of people, the Bohr model is their mental image of what an atom looks like. that planetary model, the nucleus in the center, electrons orbiting outside. It's very useful for explaining emission spectra, and that's why we still teach it, even though it's no longer the accepted model. It gives us this idea of energy levels, allows us to explain the emission spectra in terms of electron transitions from a higher energy level to a lower energy level, from an excited state to a ground state. But the electrons cannot travel in fixed circular orbits. That idea just doesn't hold up, and that led to further developments in atomic theory. So the modern model of the atom. I'm going to do a whole separate webcast on the modern model of the atom, the quantum mechanical model. Subscribe to my channel so you get all my latest videos. Leave a comment, like the video, and study chemistry every day. That's how you get better.